Hi everyone, I'm Andrea Valenza, and today I will present Never Trust Your Victim, Weaponizing Vulnerabilities in Security Scanners, a joint work with Gabriele Costa and Alessandro Armando. The main motivation behind this work is that we often see targets as our victims, as passive entities, and we often do not expect them to react in some unexpected ways, as we say. And so we often underestimate the risk of performing a network scan. And scanners are not immune to vulnerabilities, as we will see in this presentation. And so we should be more careful when we scan a target. The contribution of this work is defining a novel attacker model. And we also define a methodology and a tool to test for these kind of vulnerabilities. And we also have several vulnerabilities that we will present, and also 2 CVEs from Rapid7. So let's start from some basic information on information gathering and security scanners. Information gathering, as the name says, is gathering information about the target. And we often gather information such as open ports and services on those open ports, and also service versions and version numbers. And so we can often go on and attack a specific version of that application if we see a known vulnerabilities for that. And security scanners help us automate this process, so we don't have to do that manually. We can just go on and perform a scan, and the scanner sends a request to the target, and then it collects and parses the response from that target, and then it creates a report. And the report will be the key for our work, as analysts, of course, need to see the gathering information. And so we have a report, and it is often built in HTML. This is an example of a security scanner, which is Nmap. And when we launch Nmap, it scans the target for known services, and we can define the -SV switch. And we can have the software version on the right here. And we can see that we have, for example, open port 80. And we have here open port 80. And the version here is Cloudflare, because the server is Cloudflare. And so we have this version, but we could have different versions here. Another basic we need is cross-site scripting. So cross-site scripting is the second most prevalent issue in web applications, according to the OWASP Top 10. And the problem with the cross-site scripting is that it attacks users of the vulnerable application instead of the actual server. And cross-site scripting is also a stepping stone for more complex attacks. And we can, once we establish a cross-site scripting, we can go on and impersonate the user, or also we can steal data, or even go on and escalate privileges on the actual session. And we see here some proof of concept payloads, for example, the classical script alert1 script, or a more complex one that we will see later. And this is the result of our proof of concept. When we launch this script on a vulnerable application, we will see a pop-up containing containing 1. So let's go on and see how we attacked Metasploit Pro and the CVEs we received from Rapid7. So Metasploit Pro, if you don't know, it's an on-premise penetration testing framework, but by Rapid7, and it's quite popular, and it works both for information gathering and exploitation, and it relies on Nmap to perform network scans. And we also have a web UI in which we can display the report, and it runs locally, and this will be important later. So how does the fingerprinting process work? So first, as we can see here, Metasploit launches Nmap with the -SV switch, as we saw in the previous slide, and on the target IP. And then Nmap starts probing, as we say, the target by launching some predefined requests. And the target, of course, can respond And for example, it can respond with this HTTP response, and it says HTTP 1.1 200 OK. And then it says server version, and it says Nginx and the actual version. Nmap receives this request and then parses it using a series of regular expressions from a file called nmap service probes. And we can see here that we have a capture group on the server header, and it means that it captures everything contained in that header. And we can see that it sends back the actual version to Metasploit. So it says Nginx 1.17.0. And we can see a sample of a report here, and this version appears in the report. So the problem here is that, as you can see, we have a tainted information flow that goes from the target to the analyst report, to the analyst browser. And this will be a problem because if our target knows that we are scanning it, it can respond with something different instead of the actual version. For example, it could send us the server header containing script alert1 script, which is our proof of concept, and Nmap will capture it, and then it will send it to Metasploit, and Metasploit will display it to the analyst, and the analyst will see this. So of course we have the infamous pop-up. So how did we achieve stored cross-site scripting in Metasploit Pro? It's not as straightforward as we said before. The problem is that script alert1 script does not work in this case. And the problem is that when we scan a target, it might take a while. So Metasploit is designed to dynamically load information as it gathers it. And so we have a dynamically updated report, and the script tags are not rendered in a dynamically loaded page. And so we have this problem, but we don't really have a problem because we can use other types of other payloads. For example, we can use the image payload here, and we can use an image tag, and we have a source set to X, which is an invalid URL. And then we have an on-error attribute, which sets an error handler to alert1. So basically, we created an image that tries to fetch the X URL, but the X URL does not exist. So it triggers an error, and the error handler for that is the alert1, so the classical pop-up. And this is the result. This is an actual screenshot of the vulnerability we found and the proof of concept from the Metasploit Pro dashboard. And we can see here that we have the list of services, and the last service is the one we attacked. And we can see a broken image there. And if we zoom in, we see that we have this image, which is the X image. If we go in the console, we can see that the browser tried to fetch this image and it failed. And when it failed, it triggered the event handler, the error event handler, and it basically displayed the pop-up. So we have the first vulnerability, and we saw that when we have cross-site scripting, we can go on and create more disruptive attacks. And we could weaponize this vulnerability in different ways. We could go using a simple phishing attack. For example, we could display a fake login form. And this form could, for example, say, okay, please just put your credentials here so we can send you the report, and the user will try and log in, and actually the form will send us the credentials for that. Or we could also try to interact with the victim. For example, we could say, oh, your report is ready, please download this PDF, or please download this application, or something else. And so we could go into the social engineering aspect of the attack. Or we could also go into something more technical and we could try to attribute the attack. So we could try to understand who is attacking us. And we could try to profile the browser. We could try to understand the browser version here, or something else that is running on the actual browser. And we could also try and enable persistence. So when the user tries to close the page or change the page, we are in the browser anyway, and we can go on attacking. And this could be for these attacks, we could use the Beef framework, for example, or we could also go on and do what we actually did and go for the more technical route and the one that requires the least user interaction. And we could go for a remote code execution and trying to take over the actual machine. So the first step was trying to perform actions from the cross-site scripting. The problem here is that we only have one scan. We assume that the user only scans us once. So we have to do everything from that single attack. And we could deploy a payload that starts by performing some actions on the browser and on the actual application. And if we had, for example, if we had another function, another feature from the Metasploit Pro console, we could try and use that to move on to the actual PC, the actual host. And luckily, we do have something like that, which is the diagnostic console. And this is a known weakness for the Metasploit Pro console, Metasploit Pro application. And the diagnostic console allows users to run commands on the underlying operating system. And you can just go and run anything to run diagnostics or to directly run some scans if you need. And the problem is that this diagnostic console runs as root because Metasploit Pro does, as stated in the documentation. And we can use this feature, but we do have something that blocks us. So the first problem is that the web UI requires authentication, and we do not have direct access to those credentials. But since we are performing cross-site scripting, we are running in the logged user session, and so we can bypass this problem. The other issue is that the console is only available on the local machine, but again, we are on the browser, so we can run commands from there. And the other problem is that the diagnostic console is disabled by default, but we can enable it from the actual dashboard. So we can use this feature to perform our attack. And this is the basic flow for the attack. So Metasploit Pro performs a scan, and our malicious target sends back a cross-site scripting payload. And this payload enables the console and then runs a command on the diagnostic console, for example, by establishing a remote a reverse shell. And we can run this command, and the underlying system connects to the target-controlled remote reverse shell. And so from now on, the target can run commands on the underlying operating system from the attacker machine. So we try to automate these vulnerability testing, because these vulnerabilities are quite hard to test. And we created Revoc, a automatic tool to test these kind of vulnerabilities. And the generalized attack model here is that since we do scan, we focused on HTTP scans. And the problem here was fuzzing HTTP responses. So since HTTP scans are so common, we created HTTP response generator. And so it was easier to create the responses as we needed. And in a nutshell, we created this two-phase approach, in which on the first phase, we created the tainted flow enumerator, and we just sent some trackers to our application. And once we found some tainted flows, we tried to understand if those flows were vulnerable or not. And so the second phase was just performing some exploitation and seeing if it landed or not on the application. These are the results for our testing phase, and we can see that we have some scans here, and 36 of these were vulnerable. And we saw that the problem was on this redirect detective scan. We can see that this is the only false positive we found. I'm sorry, the only first negative we found. And the Revoc did not find this vulnerability, but after we manually tried to confirm this vulnerability, we saw that the script was indeed, the application was indeed vulnerable, but the Revoc did not have the right payload to test for that. And so we went on, and first we exploited it manually, and then we created new payloads to test for this kind of vulnerability. So now Revoc is able to test for that. It was not before, but now we integrated it in our testing environment. And on the right, we can see the distribution for vulnerabilities in the different fields that we tested for. So moving on for some future work, we try to extend these from the HTTP domain. We try to extend to different domains, for example, the DNS domain. And these are my current DNS settings. As we can see, we have a TXT field with script alert one script alert high script in this case. And I wanted to see if some DNS checker were vulnerable to that. And indeed we saw that many DNS checkers were vulnerable to this attack. And so by concluding this work, the contributions for this work were defining an overall attacker model for security scanners. And during this work, we found 2 vulnerabilities in Metasploit, in Rapid7 Metasploit Pro. And we also implemented an automatic tool to test for these kind of vulnerabilities. And we found 36 out of 78 vulnerable scanners. And with this, I would like to thank you for your attention. And if you want to go on and see how these vulnerabilities work, I leave you with some further readings here and my contacts. Thank you for your attention.